Welcome to Empowered Learning. This is the third and final video in the video series for reduction of order. This last example will be an example to where it will start off to look like it's relatively easy to do, but you'll see that we're going to have a lot of things that we need to pull in from pre-cal and Cal A and or Cal B to be able to get through this particular problem to be able to solve it for the function y or another function y that will satisfy this differential equation. Now, again, just as in the other videos, we see here that this is a second order linear homogeneous equation because, again, we have the y double prime, y prime, y. All of our coefficients here are either functions of x or constants. And the homogeneous part comes from the fact that the right-hand side of this function is equal to 0. So we see here we're given that y sub 1, which is x plus 1, is a solution. And what we want to do is find what is going to be the corresponding y sub 2, which we're going to define as just u times y1, which will be u times x plus 1, which will just be ux plus u. Okay. And of course, what we need to do is find out what y sub 2 prime and y sub 2 double prime will be, the first and second derivatives, and substitute those into our equation. So let's go ahead and get started with that. So we are going to do y sub 2 prime first. And of course, we're just taking the derivative of what we have here. So this will just be, since u is going to be a function of x, we'll treat that as a function. So it'll be u prime x plus u. And then, of course, the derivative of x is just 1. So that'll just be u here. Plus derivative of u is just u prime. And so that is what y sub 2 prime will be. I'm just going to rearrange this because it'll help me with grouping later. All right, so now we need to find out what y sub 2 double prime is. We're just going to take the derivative of the derivative here. So this will be u double prime times x plus u prime times derivative of x is just 1. Plus derivative of u prime is going to be u double prime. Derivative of u is just u prime. So here we see that we just have u double prime x plus u double prime, and this will be plus 2u prime. So now that we have that, we can substitute this information into our ODE here. And so just to keep everything together, I'm going to do it term by term. So we're going to start off here with 1 minus 2x minus x squared. And matter of fact, I'm going to back this up and want to do it in different colors here so that you can follow a little bit better. All right, so for this first one here, I have 1 minus 2x minus x squared and times y sub 2 double prime. And we'll just copy that. And of course, y sub 2 double prime, that is just going to be everything that we see here. So this is u double prime x plus u double prime plus 2u prime. And now we just need to multiply all of that together, and then we're going to group everything in terms of u double prime and u prime and u if necessary. Okay. So we'll start off here, get rid of that equal sign there. We'll just multiply everything by 1 to start off with. So that'll just be u double prime x plus u double prime plus 2u prime. Next, we'll multiply everything by minus 2x. So this will be a minus 2x squared u double prime, and then minus 2x u double prime, and then a minus 4x u prime. And then lastly, we'll multiply minus x squared times all three of these terms here. So this first one will be a minus x cubed u double prime. The next one will be a minus x squared u double prime. And the final one would be minus 2x squared u prime. And then finally, we'll group everything in terms of u double prime, u prime, and u. So for u double prime, we have term with x plus 1 minus 2x squared minus 2x minus x cubed minus x squared. I believe that's it for that one. And now everything in terms of u prime. So skip, we have 2, skip, minus 4x, skip, minus 2x squared. So all of this again will be equal to 1 minus 2x minus x squared times y sub 2 double prime. And we will circle this because we will need to refer to it again. All right, so now let's do this second term here, which is 2 times 1 plus x y sub 2 prime. So I'll do this one in green here. So we got 2 times 1 plus x times y sub 2 prime, which is the same as 2 plus 2x times, and of course y sub 2 prime is just u prime x plus u prime plus u. And now we just multiply. So I'm going to multiply these first three terms on the right by 2. And then I'm going to multiply them again by 2x. So it should be 2x squared u prime for the first one, and then plus 2x u prime for the second one, and then 2x or 2ux for the third one. And then we're going to go ahead and group all of this in terms of, in this case, u prime and u. So all terms with u prime, I have 2x here, got 2 here, skip, got plus 2x squared here, plus 2x here, and skip that one. So everything in terms of u, I got a 2u here, and I got a 2, sorry, that should just be 2. So let me erase that. And then plus, this is just 2x. And so now we have all that organized. So we will circle this. We'll refer to that again as well. And then the last term, which will just be the minus 2 y sub 2, I'll do that one in, let's see, do that one in brown, yeah. All right, so minus 2y sub 2 is just going to be minus 2. And of course, y sub 2 is just going to be ux plus u. So this is going to be ux plus u. And we're going to rearrange everything in terms of u. So we're going to pull the u out and multiply the negative 2 in. So this would just be that. And again, we will circle this because we're going to refer to it. All right, so the first thing that we want to do is we want to check to see that every term that is in terms of u, when we add all of them up, they should cancel out to 0, okay? And so here, if you see here, we have 2 plus 2x. Here we have minus, oh, so yes, this should be a minus here. So, yeah, so that should cancel out, but I'll put a plus here instead of a minus. So that's a problem. So I'll go ahead and fix that. Okay. So these two terms, whenever we add all these three things together, should cancel out to 0. So all we're going to have left is just everything in terms of u double prime and u prime. Okay. And so I'm going to go ahead and put that together now. So we'll go ahead and take care of this now. We know if we add all of these up here, that these two terms will cancel. So therefore, whenever we put this all together now, let's get rid of that. So we put that all together. This will imply that, and now we're going to group everything in terms of u double prime and u prime. So I'll come here to my very first term, and I'm just going to literally copy what I have here. I'll worry about, trying to condense everything and combining like terms later. So I've got x plus 1 minus 2x squared minus 2x minus x cubed minus x squared. And now I'll come here for this one, and I see I don't have anything in terms of u prime, or u double prime, so I can just skip that. Now I look in terms of u prime, and I have 2 minus 4x minus 2x squared. And down here I have plus 2x plus 2 plus 2x squared plus 2x. And here, since all this canceled out, our minus 2y sub 2, we don't have to write that down, so all this will equal 0. And so now we'll go ahead and combine like terms here. So as far as x squared is concerned, I have minus 2x squared minus x squared. That's going to be minus 3x squared, but I also have a minus x cubed here, so I'll put that first. And then I'll do that. As far as x is concerned, x minus 2x is going to be minus 1x. And then the last thing I have there is a plus 1. Okay. Now for the u primes, I see here that I got minus 2x squared and a 2x squared. So I'm just going to do some canceling here. Let's do it in this color. So this and this will go. What else do we have? I see I have a minus 4x here and 2x and 2x. So this will cancel these two terms out. And then I see the only thing I have left is 2 plus 2, which is 4. So that's all I need to write here. And that is equal to 0. And so now I see that I do indeed have something that's going to look something like a separable equation if I was to let my u prime be v and my u double prime be v prime. Okay, so we're going to go ahead and do that now. And let's switch colors here. So we're going to say let v equal u prime. Then this means that v prime is going to be u double prime. Okay? And this in turn means that I'm going to have v prime times minus x cubed minus 3x squared minus x plus 1 plus, and this is going to be 4 u prime here equals 0. Oh, sorry, v. Let's get rid of that. All right. So now that we have all that in place here, we can go ahead and do algebraic manipulation to this equation to just try to solve it for v. Okay. So therefore, we'll have v prime and have all this stuff here equals minus 4v. And what we'll see here is that if we rearrange this, then this will be v prime. Actually, you know what, before I do that, let's change this v prime here to dv over dx, because it'll make it easier for us to do the algebraic manipulation there. All right, so we're going to say this is dv over dx. And so now, when we do this, this will end up being dv over v. So we're going to take this v, divide it over. We're going to take the dx and multiply it on both sides. So this will be minus 4 dx. And then we're going to divide by all this business here. Okay. And if I factor out the negative out of the denominator here, then I'll end up having a positive 4 times dx here. And this will be x cubed plus 3x squared plus x minus 1. Okay. And of course, the reason why I'm saying that it will be that is because, of course, that will be minus here. And this is like that being minus. And of course, negative divided by negative is positive. All right, so now essentially have dv over v is equal to all this business here. Now it looks like we have something that's relatively easy to deal with. Okay. Now, in looking at this, of course, we know we need to integrate both sides, right? And we're looking here and we're saying, if I could factor that out, then life would be easy for me because at that point, I could use partial fraction expansion and I'm good to go. If we look a little closer here, we see that we have 4 terms. So we would want to try a factor by grouping, but we would see that's not going to work. Okay. So in this situation here, what we have to do is kind of go back to our pre-calculus algebra or college algebra days and use something called the rational zeros theorem to see if we could factor this out. Okay. And so that is what we'll do to figure out what this will factor into. Because if you try to do it any other way, it's not going to work, at least not any way that I know of. So here, I'm just going to go ahead and take care of this left side right here so that you don't have to worry about doing it later. And for the right side here, this will be 4 times integral of all this business here. And we'll just say dx like that. And this is what we want to know. All right, so using the rational zeros theorem, what the rational zeros theorem says, and I'm going to do this in a different color here. So let's Try to pick a color here that won't be too bright. Let's do purple. Yeah, that would be a good one. That almost looks like what I have, so let's pick something else. All right, a little better. All right, so note. So if we are going to factor this out, we can use what's called the rational zeros theorem, okay? And the rational zeros theorem says that if this particular polynomial has any rational number zeros, and that means that if we have any values of x that can be written as a fraction, such that when I plug it into that particular polynomial, it'll end up equaling 0. The rational zeros theorem says that if I have a polynomial that has all rational number coefficients, which basically says all my coefficients can be written as a fraction, and that meets that criterion here, then what I can do is come up with a grab bag of possibilities of what those zeros might be, okay? The rational zeros theorem doesn't guarantee that this list of possibilities will work, but it says that if you have any rational number zeros, it will be in this list, okay? And so how you get that is you'll say, let these zeros be all factors of a sub 0 divided by all factors of a sub n. And what a sub 0 is the last term, okay? The coefficient for the last term, which in this case is going to be the 1 or -1 here. The factor of a sub n is going to be the first terms here, which is going to be 1. So here we know that the factors of -1 is just going to be plus or minus 1. Factors of 1 still just plus or minus 1. So, and we normally do all combinations thereof, but of course, since we just have plus or minus 1 and plus or minus 1, of course, there's only 2 possible rational zeros, which is going to be positive or -1. So what we can do here is plug in these values to see which one, if any, would actually end up being a 0. One way that we can quickly do that is to do synthetic division here. And so to do that, I'm going to do both of them here just to kind of show it. So here we'll use 1 as the first 0, and we'll put it in this little half box here. And over here, we're going to list all of the coefficients of this particular polynomial in descending order. So here we have a 1 for the x cubed term, a 3 for the x squared term, a 1 for the x term, and a -1 for the term with no x in it. Now, if we had something here where, let's say, we were missing an x squared term, you would just put a 0 in its place, okay? All right, so from there, we're going to come down here and then make another half box here. And this box here will be our remainder box. And so one of the things that we know about a polynomial is that, of course, if we, whenever we're doing synthetic division, rather, is that whatever ends up in the remainder box is what that actual polynomial would be equal to if you evaluated it. So here, what we're actually going to find in this box is going to be what f of 1 actually is, which is whatever this particular polynomial is whenever we plug 1 into it. So in doing this, what we want to see here is a 0, because if we see a 0 here, then what that lets us know is that f of 1 is 0, and thus 1 is a rational 0 of this particular polynomial. If we see a number other than 0, then we know, hey, that's not it. But at least we do know what this function is evaluated at 1. So let's go ahead and do it. So to perform synthetic division, we take whatever number is here and we bring it down, and then we do a series of multiplication and adding. Okay, so here we say 1 times 1 is 1, and then we add. 3 plus 1 is 4. Then we do it again. 1 times 4 is 4. 4 plus 1 is 5. And then 5 times 1 times 5 is 5. Add -1 and 5, we get 4. So what we see here is that 1 is not a rational zero of this because we didn't get a 0 here. So we're hoping that -1 actually works. So we're going to repeat this process here. Half remainder box here. Bring this down. And -1 times 1 is a -1. We add, of course, 3 plus a -1 is the same as saying 3 minus 1. So that's 2. Multiply here. -1 times a +2. So -2. And we add -1. And then, of course, -1 times -1 is a +1. Add, we get 0. So here, get lucky. Great. And so what this tells us is that x equals 1, or sorry, x equals -1 is a rational zero. Now, what does that mean for us? Okay. What that means for us here is that if x equals -1 is a zero of our polynomial f of x, then that means that x plus 1 is a factor. Okay. So what that tells us here is that therefore we know that x cubed plus 3x squared plus x minus 1 is going to be equal to x plus 1 times something else. Okay. Now, the great thing about doing synthetic division is that synthetic division lets us know exactly what that other something else is. Okay. And we actually have the coefficients of it here in our quotient. Okay. I'm going to change colors here momentarily. So here we had a polynomial of degree 3. And when we did this -1 here, that was effectively like us dividing this polynomial by x plus 1. And so what we end up here with is a polynomial of degree 2. So this is the x squared coefficient. That is the x coefficient. And this is the number coefficient. So what this question mark here actually is, it'll actually end up being x squared plus 2x minus 1. All right, so we'll write that here, x squared plus 2x minus 1. And we'll go ahead and switch this back to here. Oh, wrong color. So back to here. Okay. And so now we know what this particular polynomial down here will factor to be. So now let's go back here and say now, therefore, we know that natural log of absolute value of v is going to be equal to 4 times integral of dx over, and now we have x plus 1 times x squared plus 2x minus 1. Okay. And so now from here, again, not straightforward to get to the answer, but at least we have, we can see the light at the end of the tunnel, so to speak. And so for here, what we can do is we could separate this by using partial fraction expansion to say, hey, well, this could be something like a plus this plus, and then for this other denominator here, let's fix that division. So for this division sign here, since we have a quadratic expression down here, and this is going to be one that we won't be able to factor out into real numbers. If we tried to, it would be complex. Then, of course, partial fraction expansion techniques tell us that we need to assume that the numerator here is going to be linear, or an expression that's 1 degree less than the denominator here. Okay, so we'll have all of that times dx. And so from here, we can use partial fraction expansion techniques to figure out what A, B, and C will actually end up being here. Okay. Now, there are some shortcuts, but because we have this particular quadratic factor here that can't be factored out, it'll get a little tricky if I try to do it. So I'm just going to stick with the traditional way of doing this and try to just use systems of equations to do it. So, and I'll do this in a different color as well. So let's switch back to green here. So therefore, we know that what we see here this is going to have to be equal to 1 over x plus 1 times all this business here. Okay. Or to put this another way, this is going to be, let's see if I'll wait to do that until we actually have the equations here. All right, so here we need to work on this left side here. And so a quick and dirty way for us to be able to get this to work is if I take A times all this plus x plus 1 times all this over x plus 1 times x squared plus 2x minus 1. So basically, we're going to multiply this first term here by x squared plus 2x minus 1 in numerator and denominator. And we're going to multiply the second term here by x plus 1 in the numerator and denominator. Okay, so if I did that, then what I'm going to end up with is what I'm writing here. All of that would be over x plus 1 times x squared plus 2x minus 1, and all this will be the same here. Okay. And since the denominators are the same, then we know that the numerators would have to be the same. Okay. And so we'll just go ahead and make sure that we note that. And of course, now from here, what we will do is actually just multiply all this out. This would be bx squared here plus bx plus cx plus c, and all that equals 1. And so now from here, I'm going to group everything in terms of x squared, x, and just constants. So for x squared, I'll have a, I have b, and that's it. For x, I have 2a, I have b, and I have c. And for just constants, I have minus a and c. And so now this 1 that's here, notice that we need to match up what's on the left side with what's on the right side, so we can kind of view it this way as 0x squared plus 0x plus 1. Okay. So of course, from here, we will have our x squared equations, our x equations, and our constant equations. So here we see that for x squared and x squared, a plus b would equal 0. For our x and x here, we got 2a plus b plus c is equal to 0. And for our constants, I'm just going to write it like this: c minus a is equal to 1. All right, so that makes that pretty simple to deal with here. So we can say here that b is equal to a negative a. Okay. And if I use that in here, then actually I should have did it the other way, but that's fine. Here I have 2a, and then of course b is a minus a here, plus c equals 0. So this just lets me know here that a plus c is equal to 0. And of course, that lets me know here that C is just minus A. And if I use that here, then I have minus A is equal to 1, which means that minus 2A is equal to 1, which means that A is a negative 1/2. Okay? So now that I know that A is a negative 1/2, then I know that C is going to be a positive 1/2 because it's negative of negative 1/2. And then from there, I also know that B is going to be minus A. And so B will also be the negative of whatever A is. So that's going to be the same thing here. So we can just say that both of these are equal to each other. All right, so now that we have all that, we pretty much know what we need to know here. A is negative 1/2, B and C are positive 1/2. So when we come back up here, we're going to put a negative 1/2 here, positive 1/2, positive 1/2 here. So therefore, our A, x plus 1, bx plus c, with this business here, is just going to be negative 1/2 x plus 1 plus positive 1/2 here, positive 1/2. Good to go here. Okay. All right, so now we can go back and let's switch colors again. So therefore, if we come back here, we were trying to figure out how to integrate what we were looking at here. Okay, so we're just going to go natural log absolute value of v is going to be equal to all this business here. So natural log absolute value of v is equal to, then here, of course, we have the minus 1/2, this plus 1/2 x plus 1/2 over all this business here, all that dx. Okay. All right, so in looking at this, we're in pretty good shape. We still have a little bit more work to do, but for the most part, we are okay. The first thing that I'm going to do to try to make life a little bit easier for us all is I am going to factor out a, I think I'll just factor out a positive 1/2 here. So if I do that, that'll just 1/2 out here, 1/2 times 4 is 2. And then that will leave me with a minus 1 here. And then plus, and this will be x plus 1 over here. With all this down in the denominator. And yeah, I don't need that extra thing there, so I'll get rid of that. And all of that times dx. Okay. So at this point, what we see here is that this first term here, we could integrate that real easy without a problem. Here, though, we still have a bit of an issue, and it's an issue only because of the fact that we can't take the antiderivative of it straight up. Okay. However, I'll switch colors here for this. Let's say, since I can't take the derivative of it straight up, let's say I wanted to use the substitution rule. Would this work? So if I come here and I say, well, let u be x squared plus 2x minus 1, then du would be 2x plus 2 dx. Okay. And from what I see here, I don't have that directly, but if I was to factor out this 2 here, do you see I do have what I need? Okay, because I got this x squared, I got this x plus 1 here, dx, and I need that. okay? And here I've already factored out this 2, but if I would have left that 2 in there, I would have been able to actually use this directly here, okay? Since I've already factored it out, we're not going to worry about it. But here, just know that the only thing that's different now is that since I have it this way, I'm going to have to divide by 2 here. And we're just going to have du over 2, or 1/2 du, is just going to be this x plus 1 times dx. So I could rewrite this in a way that's going to work well for me. And so because of that, I should be able to take the antiderivative of both of these relatively smooth. So we'll go back to the black color and go ahead and do that. All right, so we have, don't like the way that V looks. So all right, so we have that, and this is essentially going to be 2 times, and we're going to be doing integral of this, and I'm just going to do it as 2 separate integrals now. And for this one, we're going to replace x plus 1 dx here with 1/2 du all over u, okay? And of course, on the right side here, this will be 2 times. For here, we would use the substitution rule here, but this is one that's common that we know. So this ends up just being negative natural log absolute value of x plus 1. Over here for this one, this will be 1/2 of natural log of absolute value of u. Okay. And so for here, this means that natural log of absolute value of v now will be 2 times. And here, what I could do right here, and I'm going to switch the placement of these. This 1/2 can be brought in the exponent here. So this would be natural log of absolute value of square root of u minus natural log of absolute value of x plus 1. Okay. And of course here, I can use my logarithm properties to rewrite this as just natural log of square root of u over x plus 1. And we know u is just going to be this x squared plus 2x plus 1. But before I do that, I know that this 2 could also be brought into the exponent for both of these. And so this can now look like just u here, because if I take square root of u and square it, I just get u. And if I take x plus 1 and square it, I get x plus 1 squared. Okay. And so now this would just be natural log of x squared plus 2x minus 1 all over x plus 1 quantity squared. All right, so doing more work here now. We're at natural log absolute value of v, and of course we just have here all this business. And of course, from our rules here, we know that if we have natural log of something equals natural log of something else, then everything that's on the inside must be equal. So here we have v is equal to x squared plus 2x minus 1. And we're here. And so this is what our function v is going to end up being. Okay. So if we look here, of course, our goal is not to find out what v is. Our goal is to find out what y is. And so we remember way back here, we said let v be u prime, or du over dx. So here, now that we're finally at this point, we're going to say that, hey, remember that this was u prime, which was same as du over dx, okay? So because of that, that means now that if we rearrange this equation here using this term and this one, we know that du is essentially just x squared plus 2x minus 1 over x plus 1 quantity squared times dx here. And so we need to figure out what u is by basically integrating both sides here, okay? Now, if we look at what we have here, again, we're kind of in a situation where this is not going to work out for me, be able to take the antiderivative of it straight up. However, we can rewrite what we see here to help us out so that we can actually do it, okay? Now, there's several different techniques that we could do. The one thing that I'm going to do to try to keep this to be as simple as possible here is I would like to, if possible, keep this as x plus 1 quantity squared down here. So I'm going to try to rewrite this so that I could force this to have an x plus 1 quantity squared there. And of course, the easiest way that I could do that is I could do completing the square. And so I'll write a note here. I technically don't have to do completing the square here, but it turns out that that's what I end up doing, okay? So here, if I was to basically say I have this, and then let's say I add 1, subtract 1, and then I rearrange this around here, I will have x squared plus 2x plus 1, this plus 1 here. And then if I had that, then I just have minus 1 minus 1. That would be a minus 2. Notice that x squared plus 2x plus 1, if we factor that, that is going to be x plus 1 quantity squared, okay? And of course, that tells me that this numerator here could be rewritten as x squared plus 1 quantity squared minus 2, okay? So what that means for me here now is that therefore du now is going to be x squared plus 1 quantity squared minus 2 over x squared plus 1 quantity squared, which is just going to be 1 minus 2 over x plus 1 quantity squared. And this is much easier for us to integrate, okay? And I'm going to go ahead and fill in all the details here because I didn't do that. So this would be your dx here, and all this would be your dx here, okay? And so now what this means is we just need to integrate what we have here. And of course, on the right side, I could just rewrite it this way. And so again here, you could use the substitution rule again for this. And just to make sure I don't miss any signs or anything like that, I'm going to do it, but we really don't need to do it here. So for here, we could let's say z, well, let's not say z here. I'll use another letter. Let's use, I don't think I have used u. So let's just do z, yeah. All right, so let z be x plus 1. So then that means dz, we take the derivative of x with respect to x is just 1. Take the derivative of any constant, that's going to be 0 here. So really this is going to be dx. So here I can rewrite this as 1 divided by z squared, or put another way, z raised to the negative 2. And then this here would just, the dx here would just be dz. Okay. So here if I did this, and I'm going to write this in this color, this will be integral of 1 dx minus 2 times integral of, and this would be z raised to the negative 2 dz, okay, based upon what I would substitute over here, okay. Now, if we did that, then of course, on this side, we would have integral of this would just be x minus 2 times the antiderivative of z raised to the negative 2 would end up being z raised to the negative 1 divided by negative 1. And then, of course, we'll have some integration constant, and I'll just call that k1 in this instance. And, of course, here this minus and this minus would multiply to be plus. And so what we would essentially have here is x plus 2 divided by z, because z raised to the negative 1 is the same as 1 over z, plus k1. All right, so now that we've done all that, then therefore the integral of u du is going to be equal to, I'm just kind of recollecting everything so that we kind of know what we're doing to get to the finish line here. So this would be, of course, the integral of du would just be u, and the integral of all this, we've already found it, which is x plus 2z plus k1. But now we need to fill in what z actually is. Well, we know that z is actually x plus 1 plus k1 here. So this is what our function u actually is, okay? Now, to make it a little bit easier to deal with what we were actually given, what I'm going to do is combine these two terms, the first two terms, to make one quotient. So to do that, I'll say x plus 1 times x plus 2 here all over x plus 1. Okay, and that'll be plus k1 there. And this will just end up being x squared plus x plus 2 all over x plus 1 equals k1. So therefore u is that. All right, and so now remember, we don't really need that constant there. So we can actually come here and say, for simplicity, let u, which is a function of x here, let that just be x squared plus x plus 2 all over x plus 1. Okay. And so if we do that, then that lets us know here that our y2, if you remember, way back at the beginning of this problem here, we said that y2 was going to be u times y1, okay? And so, of course, our y1 was x plus 1, so we're going to use this here. So we're just going to take whatever we have for u and multiply it times x plus 1. Okay, so we have u times x plus 1, which is just going to be all this business here times x plus 1, of course that over 1, and of course these x plus 1s here will reduce to 1. And so our final result that we have here will be x squared plus x plus 2. And that will be what our other function, or our fundamental function for our basis of solutions, will be. Okay, I know it took us a while to get there, but we finally got there. So therefore, now I'll switch colors here since we're finally at the end of this. Let's do this in green. So therefore, we know that our general solution here is going to be C1 times, and of course our y1 here was just x plus 1, plus C2, and our other function here is going to be x squared plus x plus 2. Okay, and just know here our basis of solutions for this particular ODE is going to be the function x plus 1 and the function x squared plus x plus 2. And again, what this means here is that these two functions, if I do any linear combination of this function by itself, or this function by itself, or these two together, and I try to find this first and second derivatives, plug that into our ODE that we were working on, it is always going to be a solution. Okay. All right. So this is our general solution here. And our basis of solutions, now that we've used reduction of order to find the second fundamental function to finish the basis, now we know all that information here. Okay. All right. So this concludes this video, and it also concludes the series on reduction of order. I know if you sat down and actually watched all 3 videos, you're like, man, this stuff takes too long. I understand, but please understand that as we move forward here, we are going to use reduction of order to study some of those second order and higher order differential equations. But know that we're going to do the heavy work first to actually figure out what to expect, so that we won't have to go through this process every single time. Okay. For certain types of ODEs that we're going to study later, we're going to know what the outcome is when we do reduction of order. So instead of us actually recreating the wheel and doing it every time, we're just going to say, hey, if we have the situation, we know that we would have to do reduction of order. Reduction of order gives us this particular type of solution for the situation, and we just use that and roll with it. Okay. But now you know actually how all that stuff happens. And of course, for those of you that will end up taking higher or advanced math to where you won't be able to have situations where you're like, hey, when we just have this, we just do that. You kind of know what it is that you're going to go through to deal with this whole reduction of order thing. And hopefully this problem gives you a good idea of at least a mid-level of difficulty of the kind of things that you'll see at that level. All right. So again, I hope that this helped to make some things clear and to help jog your memory on some of those concepts that you may have forgotten from first year calculus or second year calculus or pre-calc. All right. Take care.